morning. We're pleased to have such a large turnout. Welcome to the first of a series of lectures to be presented by Professor Paul Emmett on the subject of coal conversion processes. Professor Emmett needs no introduction to most of us. He has been a consultant to the Oak Ridge National Laboratory essentially as long as there has been an Oak Ridge National Laboratory. We know him to be a very capable and competent authority on the subject of catalysts, and very recently he has done a great deal of work in coal conversion processes. We are very pleased that Professor Emmett has consented to present these lectures. It's very fitting that he should be the first to kick off our series of what we hope will be a continuing series of lectures and other information that will be useful to people in our coal conversion and other related work. The procedures for the lectures are about as follows. Professor Emmett will be talking for an hour, beginning now and again at 2 this afternoon. Also on tomorrow there will be lectures at 10 and 2, and on Friday the lectures will be at 9 and 2. Professor Emmett has already arranged for distribution of the lecture notes for the first lecture. It may be that there aren't enough copies to go around. We can certainly arrange to make more if there are not. Professor Emmett will be prepared to answer questions for at least about a half an hour after each of his lectures, and he can arrange for private discussions with us throughout the course of his visit here at the laboratory. Professor Emmett?
I'm glad you got a portable mic. I'm very glad of the chance to come down and talk a bit in regard to coal. I want to relieve you of any misapprehensions as to my being a coal expert, because I'm not, but I do know a little bit about catalysis, and I sort of consider the coal problem as one grand catalytic program for the next 15 or 20 years. So with that in mind, you will pardon me if I emphasize some of the catalytic aspects of the refining. Specifically in the lectures, as you will see in this set of notes that is available, I'm going to divide the subject up into 6 lectures. In the first one, I'm going to include a discussion of physical and chemical adsorption, because physical and chemical adsorption are both important in measuring surface areas, pore size, and indeed in the catalytic activity itself. This will be combined with a discussion of the structure of coal. The second lecture covering pyrolysis and chemical treatment, including some work on solution in coal. These lectures, such as number 2, of course, are entirely from the literature, so if the literature is wrong, you'll forgive me if I make mistakes, but I'll try to be as accurate as I can. The third lecture is on gasification of coal, carbon dioxide and hydrogen. In the fourth, I'm going to summarize briefly all of the known catalytic processes that I know anything about for utilizing carbon dioxide and hydrogen. These include the all-important Fischer-Tropsch synthesis, or at least it was important at one time, methanation, methanol formation, and so forth and so on. Then in the fifth lecture, we'll consider in detail the hydro liquefaction of coal. And finally, in the last lecture, I've dumped everything in regard to sulfur, the desulfurization mechanisms we know anything about, the work on scrubbing of sulfur. I even put the underground gasification in here on the basis that it's one way of dodging the sulfur problem, because it's very easy to take sulfur out of gas. And if you're going to bring gas up out of the ground, you don't have any large desulfurization problem. The discussion of coal and energy situation usually starts out with a prolonged presentation of the facts as to the coal difficulty. Recently I heard Ed Teller, as a matter of fact, of interest to you perhaps. He's lecturing now on coal, and he treats coal as, he treats the energy crisis as a disease, and he goes through the diagnosis of the disease, the symptoms of the disease, and finally the cure of the disease. It's a very effective presentation. But I assume that everybody here is quite familiar with the energy crunch, with the things that we are facing, with the reasons for having to go to coal, and with the importance that coal is going to play in the years in the future. Incidentally, while I'm introducing the subject, I might emphasize that I'll be minimizing the economic factors because I don't know anything about them and don't pretend to know anything about them. Economic calculations on these various processes will be certainly at the heart of the decisions as to what pilot plants will be built and what processes will be used. Another item that's very obvious to me as well as to anybody who thinks about the subject is that nobody's going to be building anything until some arrangement can be made to make sure that the builder isn't going to lose a lot of money. I can visualize elaborate plants being built for coal refining to produce gasoline, natural gas, and so forth, and then having certain powers cut the price of oil by $2 or $3 a barrel and bankrupt all of the plants. So I think there's some economic factors that have to be taken care of before we're going to be building any plants to produce gasoline or gaseous products. But as I say, that's a matter for the experts in such fields, and I'll gladly pass them by. So to begin with then, I want to turn attention to a discussion of physical and chemical adsorption. One of the delights of my brief contact with coal, and incidentally I've done no research in coal. I've given a lecture series on coal, but the coal is all secondhand material to me. The part that I am familiar with is to do with the surface studies and catalytic aspects of the subject. One of the most interesting things that I've run across has to do with the surface area of coal. So as a preliminary to that, I want to discuss physical and chemical adsorption to make clear to everybody here. I think most people here probably are expert on physical and chemical adsorption and their applications to surface area and pore size measurements and catalysis, but I'll go through the story anyhow. And I think I have most of this on slides, so if I may have the first slide, please. This is a summation of chemical and physical adsorption properties, the criteria by which one can differentiate between physical and chemical adsorption. Physical adsorption, as is well known, occurs at any temperature near the boiling point. It occurs at any temperature, whether it's near the boiling point or not, but large amounts of physical adsorption will appear near the boiling point of the particular adsorbate involved. Chemical adsorption, on the other hand, is one that occurs usually at high temperature, keeping in mind that chemical adsorption is really a chemical reaction between a gaseous component and the solid material. One can see that it will take place in the same range in general in which chemical reactions take place, namely at higher temperatures. All solids will show physical adsorption. The walls, the carpets, the chairs, everything else has physical adsorption of air on it at all times, something the order of 1% of a monolayer. But the solid, it extends to all solids, and the chemical nature of the solid is not involved. Chemical adsorption, on the other hand, will occur only in those systems in which you would expect bonds to be formed. Nitrogen, for example, on silica gel at liquid nitrogen temperature would not be very likely to form any chemical bonds. On the other hand, nitrogen on iron at 500 degrees centigrade would be very likely to form such because we know the nitrides exist. All gases will undergo physical adsorption. I've seen a few bizarre cases in which physical adsorption simply didn't occur. The only one I recall right now is one that George Halsted showed for krypton on sodium spheres at liquid nitrogen temperature. Krypton won't adsorb. I don't know why. Under this, only reactive gases, it used to be very easy to point out that the rare gases, helium, argon, and so forth, would never adsorb, and that one had only to consider the other gases and to consider the chemical properties of the gases with respect to the solid as to whether you got chemical absorption. I'm not so sure of myself anymore. We studied extensively the fluorination of xenon over nickel fluoride as a catalyst. And though we didn't get to the point of proving that we had chemical adsorption of xenon, it wouldn't be out of reason to expect that if the xenon is going to react with the fluorine, there may also be some chemical adsorption of xenon. So there may possibly be a few rare gases such as xenon, and I don't think I'll go any farther than xenon, that do undergo chemical adsorption on some surfaces, such as fluorides and so forth. But for the most part, the rare gases are still examples of those things that don't undergo chemical adsorption. Physical adsorption is characterized by low heat of absorption, usually somewhere near the heat of liquefaction, perhaps a factor of 2 bigger than the heat of liquefaction. Chemical adsorption may have high heats running to 10, 20, 30, 40 kilocalories per mole, similar to the heats of interaction of gases with solids, of gases chemically to form compounds. Finally, this last characteristic is that physical adsorption is very fast. Now, this is true provided the surface on which the physical adsorption is taking place is readily accessible. But obviously, if the surface is located down a connection of pores, it could take considerable time for physical adsorption to take place. All of you know what Vicor is. Well, I think we were among the very first to make adsorption measurements on Vicor. And the first piece of Vicor that we got from the Corning Glass Company was a little section, looked like a section out of a glass plate that had been on the top of a desk. It was about a centimeter square, 5 millimeters thick, sort of a translucent type material. We took that as was and measured adsorption of nitrogen, liquid nitrogen temperature. And we got adsorption curves, but each adsorption point took 24 hours to equilibrate. Now, this is a length of time that it was involved in nitrogen molecules diffusing down pores 30 angstroms in diameter for a distance of 2.5 millimeters. This same material, when ground to 200 mesh, gave exactly the same adsorption curve, but each point took 3 minutes instead of 24 hours. So you see, physical adsorption can be slow if there's a connecting capillary system through which the gas has to diffuse. Chemical adsorption is usually slow, just in the sense that most chemical reactions involve energies of activation. So most chemical adsorption involves an energy of activation. But to all of these things that I've mentioned here, there are exceptions that we may run across from time to time. For example, carbon monoxide chemically adsorbs on iron instantaneously at minus 195 degrees. This means the energy of activation can't be more than a kilocalorie or so at the most to account for the experimental results. On the other hand, nitrogen doesn't adsorb short of 200 or 300 degrees centigrade. So there's an energy of activation for nitrogen chemisorption, but not for carbon monoxide chemisorption. The heat of binding of carbon monoxide is high, around 35 kilocalories, so it's really chemical adsorption, but the rate happens to be very fast. Well, this gives you a general idea of what we would expect for physical and chemical adsorption. Next slide, please. This is a historic slide that I like to show in connection with physical adsorption because it represented our first search for a method for using physical adsorption to measure surface areas. And the reason I'm discussing physical adsorption is that there are several important uses of it. One is to measure surface areas of material, and we'll see a little later that we can use it to measure surface areas of coal, and also pore size, and it can be used for pore size measurements on coal likewise. These are isotherms simply representing the volume of gas adsorbed as a function of pressure under the conditions indicated. And you will see that for the most part they consist of curves that blend into straight lines, all down here in about the same general location. So in the very early work we decided that this might be a place corresponding to a monolayer. We drew a straight line through to the intercept here. The intercept was point A, this was point B, the middle point here was point C, the upper end of the curve where it pulls away from the straight line was point D, and the intercept of this extrapolation was point E. This, therefore, is called point B, and we call that the point B method, namely the estimation of the monolayer just by picking the linear part of these adsorption curves. I might digress just to point out the surprise we got when we ran carbon monoxide. As I told you, carbon monoxide doesn't have an energy of activation for its adsorption. Witness the fact that the adsorption isotherm determined going up in this direction agrees nicely with the desorption curve. In other words, all of the chemical adsorption, which is the distance between this curve and this, had taken place within the first short time required to take these first two adsorption points. Again, to digress for a moment, because one shouldn't include such things in the lecture, it's interesting that when this paper was sent in to Dr. Lamb back in 1933 for publication, it was turned down flat, because there were people on the staff, I think, who were horrified at the idea of this being a monolayer out here. They wanted it down here, up here, someplace, I don't know where. But the fact that the chemical adsorption volume was equal to the volume that we claimed for physical adsorption was a convincing bit of evidence that enabled us to get the paper published. So even in those days, which is many, many years ago, there were troubles on publication. The other thing that I'm going to mention in passing, because it may be of interest to some of you who might be metallurgists, is the fact that if you put oxygen in, I don't have an oxygen curve here, but if you put oxygen in, you get not one chemisorph layer, you get 10 layers, going up about 50 feet into the air if we plotted the first oxygen curve. But after those 10 layers are completely covered with oxygen, then one can run oxygen on curves like this and get the same kind of curve we have here. This is often forgotten, but I'm very suspicious of any experiment showing oxygen pickup on any metal unless they consider that it also goes in 2 or 3 layers, sometimes many more layers, many more layers than that. Well, so these isotherms were used, as I say, to give an empirical method for arriving at a volume of gas that we considered a monolayer. And by calculating in obvious ways the size of the molecules, we can calculate out the surface areas. Next slide. Soon we collaborated, Brunner, who was working with me, and I collaborated with Teller to produce an equation representing these S-shaped curves. That's this equation 1 that's become known as the BET equation and represents simply a plot of the pressure at which adsorption measurements are made, the equilibrium pressure of the liquid, liquefaction pressure of the liquid we're using at a particular temperature, the volume adsorption, and the V sub m is the volume of gas required for a monolayer. C is a constant involving the heat of adsorption on the surface. And a plot of this versus the left-hand side enables you to evaluate both V sub m and C, as shown in the next slide, to give linear plots, as I say, from the slope and intercept of which one can obtain surface area, one can obtain volume of adsorption corresponding to a monolayer, and then by knowing the size of the molecule can get the surface area of materials involved. This is all work so far here that has been presented back prior to 1938. I'm glad to say that this so-called BET method is still accepted, and I think you will find papers from all over the world using catalysts or porous surfaces mentioning surface areas. It hasn't become quite so common in coal technology yet, but I hope that it will become more so, because surface areas of coals, as we'll see pretty soon, are very interesting indeed. Next slide. Some of you may have worked with zeolites or with charcoal, and if so, you've run into a realization that it is difficult to tell the amount of surface of charcoal and zeolites, because you don't get these S-shaped curves, you get flat curves, Limeur type curves. And the question as to the monolayer position is rather a perplexing one. There is another reason for having difficulty with surface area measurements of material of molecular size. This paper published by a couple of Englishmen, Neil, I think, and somebody else, I forget the names. Incidentally, all of these notes are well documented with references. As a matter of fact, you'll find when you get the six lecture notes series that there'll be portions of the work that I'll have to skip because of time limitations, but they're all documented there, outlined, and references given, so I think that the references may prove to be very helpful to you. These particular authors pointed out that if molecules are adsorbed in capillaries of their own size, or even of twice the size, the area blocked off by each molecule is not the flat area of a molecule sitting on a surface, but it's the circumference around this capillary that is blocked off by these molecules. And it turns out that this is 3.66 times as big as the flat area that would be blocked out by molecules sitting on the surface. Consequently, the volume of nitrogen adsorbed in zeolites and in charcoal may give only a minimum value for the surface area. The real surface area may be considerably larger because molecular size capillaries exist in both these materials. But these are complications that one arrives at, and we'll find out a little bit more about this when we discuss coal. Next slide. To illustrate this business of the small pores, these data presented by Dubinin are rather interesting. Zeolites have a known crystal structure, as you're well aware, and therefore by sitting down with yourself and thinking about the structure of a zeolite, and therefore the area of the zeolite, you can calculate out the true area that the zeolite should occupy, that should possess. Then he compared this with the adsorption data for various gases on zeolites, and you come out with a factor over here that to get the true area, one would have to multiply by factors that are shown here. Now, they're not as high as 3.66, but they're getting up pretty close to it. Even nitrogen, for example, the area that you get, these are given in terms of weights of material per milligram or per gram of sample. But the essence of it is that the area that you get is only 1/2 this divided by 2.03. These other molecules give you an area that is this divided by whatever factor shown here. So this illustrates the fact that for zeolites, the surface area that you get is going to be smaller than the true surface area. Indeed, it becomes sort of a question as to what the surface area really means when the holes are as small as they are in zeolites. This will all come up again in our coal discussion. Next slide. So much then for physical adsorption as being a very important tool for measuring the pore size, or rather the surface area of finely divided or porous solids. Just a few remarks in regard to measuring the pore size and the pore distribution. Again, turning to the material Vicor, which is a very convenient form of material with a known pore size and rather uniform pore size, we have here nitrogen adsorption isotherms on such porous glass at two different temperatures. You'll notice they're characterized by an adsorption portion going on up here to high relative pressures, and then a desorption pressure with desorption point portion of the isotherm with a very sharp and steep desorption at a particular relative pressure. This simply shows up the uniformity of the capillaries. If there was a broad distribution of capillaries, this would be a broad distribution on this desorption curve. Well, one can get estimates from various ways. If one uses straight Kelvin equation, one can estimate the pore size from the relative pressure at which this desorption occurs, knowing the surface tension of nitrogen and so forth and so on. But desorption curves of this type, or of any type, are the ones that were used by Barrett, Joyner, and Halinda to work out a method for calculating the pore distribution. I won't go through the method, but I will show you the next slide. The type of distribution that they obtained on a sugar char used for decolorizing sugar. I like to show this because it has a peak in it here, double peak with a valley in between, showing a bimodal distribution of pores, the radius of which in the one case is somewhere here around 80 or 90 angstroms, and in the other case down around 25 or 30 angstroms in size. The solid points represent the surface area gotten by the mercury porosimeter, which is another method for measuring pore distributions, except that one has to get this last point down here, one had to use a pressure of 30,000 pounds per square inch. And if you want to push it down a little bit further to conform to the nitrogen runs, measurements have been made as high as 100,000 pounds per square inch. This is simply the pressure necessary to force mercury into a tiny capillary. You're all aware of the fact that when you put a capillary tube into mercury, the mercury is depressed. Well, Washburn pointed out a number of years ago from the Bureau of Standards that if you put pressure on that mercury, you will force it back up into the capillary. And he worked out equations to show the relationship between the pressure necessary to force mercury into capillaries and the size of the capillaries. And that essentially is what is involved in mercury porosimeter measurements. The agreement between these is rather reassuring. There's still lots of work being done on pore size. When you consider that this application is to a material that may consist of a lot of crystalline materials all piled together, and that the pores are not cylindrical pores at all, but they're jumbles that are left between the particles, it's remarkable that one gets even this type of agreement. But though the subject is not closed, the surface areas, the pore size arrived at by the means of either the nitrogen curves, desorption curves, shown with a solid line, or the mercury porosimeter within its range of applicability, are generally believed to be fairly accurate presentations of pore distribution. And we shall again meet this in connection with coal pretty soon. Next slide. Now, I mentioned that we wanted to say something about chemical adsorption. Chemical adsorption is going to be important because it is the type of adsorption that is involved in all catalytic reactions. And as we study the various processes for treating coal, we'll be concerned about the chemisorption of organic molecules containing sulfur, we will say, on catalysts that are going to be used for desulfurization. The adsorption of carbon monoxide, hydrogen, hydrocarbons, all of these factors will come in consideration of the catalysis of coal processes. This, for illustration, is the adsorption of hydrogen on an iron synthetic ammonia catalyst. If one exposes a catalyst at minus 200 degrees to hydrogen, one gets this kind of an adsorption isotherm, which is generally considered to be physical adsorption. You see, hydrogen boils down at 20 degrees absolute or so. This is quite a bit away above its boiling point, but there still is considerable physical adsorption which disappears in here somewhere. Going to a little higher temperature, a chemical type adsorption comes in. There's still higher temperature in other chemical types. So there are two types. We call this type A and this type B. We assigned those designations 40 years ago, and I regret to say we still have to call them type A and type B because we still don't know what they are. There's a difference between these, but whether it's the position of the hydrogen atoms in the iron, like some of them being on the top layer of atoms and some of them down on the body-centered atom, or whether it's the type of binding, we know both of them are dissociative. There's a lot of evidence for that. We know the heats of absorption and so forth, but we really don't know the difference between these two. And to make matters more complicated, though I'm not bothering with it, this is for a catalyst containing potassium oxide, aluminum oxide as promoters to iron. So it's an iron, potassium oxide, aluminum oxide surface. If you leave out the potassium oxide, this curve doesn't come down here, but comes over like this, goes scooting back. In other words, there's a third chemical type adsorption called type C adsorption that's capable of the hydrogen-deuterium exchange and is therefore a dissociative type adsorption almost certainly. So there are three types of adsorption of hydrogen on some systems, on some iron catalysts, and indeed in some cases there may be even more chemisorption types. But chemisorption in general occurs, as I say, at higher temperatures, has a high heat of adsorption, and is related to the chemical interaction of the adsorbate with the adsorbent surface. Next slide. I said that chemical adsorption was essential to all catalytic reactions. We were rather embarrassed in the petroleum field when we were unable to find any chemisorption of saturated hydrocarbons on the catalysts that are used for making all of your gasoline today, cracking catalysts. This represents some of the early work that we did years ago on the adsorption of butane as a function of temperature. And I'll only say that these first adsorption curves turned out to be phony because they were due not to butane but to traces of butene that were in the butane. When we finally purified our butane adequately, all of the adsorptions in one atmosphere right down along the baseline here, all we could say is there was no greater than 0.05 of a cc per gram. So we had to resort to a radioactive tracer method to prove the existence of chemisorption of hydrocarbons on silica alumina catalysts. The next slide shows the results of these tracer measurements, and I'll just point out that the adsorption shown up here amounts to about 0.003 of a cc per gram. This is a chemical adsorption of the hydrocarbon on the surface of the cracking catalyst and relieves our feeling in regard to there being chemical adsorption. It turns out that the cracking catalysts don't require very many active sites for the cracking, and therefore the positions on which the reaction takes place represent a small fraction of the surface. The adsorption, chemical adsorption, is accordingly small, but nevertheless it's finite and can be measured when we use radioactive butane for the measurements. So it is still a truism that every chemical reaction, every catalytic reaction that takes place involves one or both reactants be chemisorbed. There is a possibility of one of them being chemisorbed and the other one striking from the gas phase and removing that chemisorbed molecule. But at least one of the reactants has to be chemisorbed, and we don't know any exceptions to this at the present time. Next slide. One application of chemisorption, other than its being involved in catalysis in a very important way, has to do with measuring the types of material on the surface of a catalyst. In making iron synthetic ammonia catalysts, one adds two promoters usually, potassium oxide and aluminum oxide, about 1% each. And in some mysterious way, these small amounts of impurities that are called promoters make the catalyst very much better than it is without the impurities. We set out to find out something about this, and if possible to find out what the concentration of promoter was on the surface of a catalyst. And chemisorption proved to be a valuable tool. On pure iron, these are the curves that I showed in a slide a while ago, cleared up with some of the other materials. This is a chemisorption of carbon monoxide on pure iron catalyst. This is a physical adsorption, so they're about the same size, and one has a complete layer of chemisorption of carbon monoxide formed on this pure iron catalyst at minus 183 or minus 195 degrees. On the other hand, with promoter present, these quantities of potassium aluminum oxide, the chemisorption is small. Turns out to be about 40% of the surface. So as a first guess, we said that 40% of the surface was iron and 60% was promoter. Now it so happens that this promoter contains potassium, so it seemed likely that it might chemisorb carbon dioxide. And the next slide shows the results with carbon dioxide. Again, pure iron giving practically no chemisorption. This one giving a considerable chemisorption, which turned out to be about 60% of the surface. So everything G'd up nicely to indicate that the carbon monoxide was adsorbed on the iron, the carbon dioxide on the promoter molecules. The iron covered 40% of the surface, the promoter 60% of the surface. This has all been confirmed with some recent work that we did on oxygen-18 isotopes. We measured the amount of oxygen-16 in the promoters on the surface by equilibrating them with H2O18 in the gas phase and noting the analysis of the finely equilibrated mixture. In other words, we could count the oxygens on the surface by using tracers, and it agreed with this 40-60 business, and since we're not talking on ammonia synthesis, I won't go into it any more deeply than that. I will, however, point out that today, in many of the catalysts probably that you're going to use in coal work, you're interested in knowing the amount of metallic surface. For example, platinum on alumina is used in some cases. The surface area of platinum is measured by exactly the same chemisorption technique, namely the carbon monoxide, not the carbon dioxide. Carbon monoxide chemisorbs on metallic catalysts and can be used uniformly to produce an estimate of the surface area of this. Some other work I happen to be connected with down at the Bureau of Mines, they've just been measuring these on the Raney nickel catalysts. They're going to be used as methanation catalysts, the ones in which you put the Raney nickel, according to the Bureau of Mines technique, as a molten material on a stainless steel tube, solidify the material, extract most of the aluminum, and then use this as a catalyst for the carbon monoxide hydrogen reaction to form methane in the methanation processes, producing synthetic natural gas. The surface area of that nickel can be measured by carbon monoxide chemisorption, or hydrogen chemisorption, or oxygen chemisorption. Oxygen's a little suspicious because it can go deeper than one layer, but carbon monoxide stays on a uniform basis on the top layer, so does hydrogen. So this really started the trend to measure the surface areas of metallic substances by the chemisorption of some suitable gas, carbon monoxide and hydrogen being the choice, and we'll find reference to those in the later work on catalytic processes. Now I think next I have a transparency. So could I have the first transparency? About 20 years ago, an Indian at the University of Pittsburgh wanted to work with me, and it was impossible because I was on the Gulf Fellowship at Mellon. We didn't accommodate people of this sort. I mean, by people of this sort, I mean postdoctorate people. At that time, they hadn't arranged for them. But he worked at the University of Pittsburgh, and I talked to him weekends anyhow. He was interested in the surface area of coal, and he found the most astounding thing. Incidentally, you'll see in my lecture notes that I've skipped now several interesting applications of surface area work, including applications of the moon samples from Apollo 11 that Holmes and Fuller obtained here. They're very interesting themselves, but hardly worth, I mean, this is not suitable to take up time with them at the point I'm mentioning, but the references are all given there. So I'm passing directly to coal. He found that when you measured the surface area of porous coal with these same kind of nitrogen adsorptions I showed in an earlier slide, there was practically no absorption. The surface area in square meters per gram for most of his coals, as you can see, are right down along this line and are designated as less than 1 square meter per gram. Now, 1 square meter of surface per gram amounts to about 2/10 of a cc of adsorbate on the surface per gram. So this is counted as an easy place to call a limit to the surface area and not worry about whether it's 1/10 or 5/10 or 1 square meter per gram. But these are all less than square meter per gram. This is what Keeney found on the sample that he measured 20 years ago at the University of Pittsburgh. However, he also measured and this was his idea, to measure the surface area at higher temperature. I'm not sure whether he suspected there was a reason for this or not, but when he did so, he found that the surface area of the coal he used was somewhere between 50 and 100 square meters per gram. This was a dry ice temperature, minus 78 degrees. Well, Walker at Penn State University has extended these measurements greatly, and in this particular slide, taken from his paper, the reference to which is given in the notes, are shown results for, I think, about 27 coals. Now, the circles, open or closed, are for samples taken at liquid nitrogen temperature. And you can see that most of them are down to square meter per gram, but there are about 8 or 10 here that have surface areas up to 50 or 100 square meters per gram by nitrogen. Now, on the other hand, when you measure the adsorption of carbon dioxide at room temperature by a method I'll outline in a moment, the surface areas of these materials are way up here and extend up for lignites as high as 300 square meters per gram, for anthracites as high as 400 square meters per gram. For the large range of bituminous coals are in the range of, what we would say, 150 to 250 square meters per gram. But all of these coals have a high surface area. Another way of visualizing this surface area is that it would correspond to the area that you had if you had little cubes of coal in the range of 100 to 600 angstrom units piled together. So we have to look at coal as a very porous material with lots of internal surface area. The details, well, the method by which these surface areas were measured simply involved the adsorption of carbon dioxide at room temperature instead of nitrogen at liquid nitrogen temperature. Now that sounds easy, but if you consider for a minute, when you measure the adsorption of nitrogen at liquid nitrogen temperature, the monolayer region, the beginning of that straight line of those curves I showed, occurs at about a 10th relative pressure. So you have to measure adsorption a little below a 10th relative pressure and a little high, a little above a 10th relative pressure. Well, carbon dioxide at room temperature has a pressure of 66 atmospheres. So a 10th relative pressure is 6 atmospheres. So you find yourself measuring carbon dioxide adsorption in a high pressure burette between 3 atmospheres and 10 atmospheres. And this is very awkward. So he made use of an equation shown in the next transparency, an equation developed by Dubinin according to making use of a Polanyi plot, in which the logarithm of the volume of gas adsorbed is plotted against the log of the relative pressure. You remember in the first BET equations we had this P over P0 as the relative pressure, simply the fraction of the liquefaction pressure at which you're measuring the adsorption. When adsorption data are plotted in that way, you'll notice you get straight lines. Now, to get the point corresponding to a monolayer, one wants to get up to about a 10th relative pressure. That's about 6 atmospheres, so around 4,000, 5,000 millimeters. In other words, you want to get up to this point on the curves. So all he does is to take adsorption data between 50 and 500 millimeters, which is nicely done on a glass burette, plot the data up in this way and extrapolate up to this region and get the volume of gas corresponding to a 10th relative pressure or whatever pressure he wishes to use as the estimate for the monolayer. When he does that in a transparency that is misplaced here somewhere, I'll find it eventually, you will find that the agreement between the regular BET values, which he got in working between 3 and 10 atmospheres, he did this high pressure work, and that gotten by this shorthand method of working at a low pressure and extrapolating is very, very good. So that one can measure, and this is a point that we all want to keep in mind, at least anything I have to do with the work down here, I'm going to urge that we have facilities for measure the carbon dioxide surface area of every charcoal on which you're making any measurements of reactivity or whatnot at temperatures at which you retain this surface area. And we'll discuss that more later. The next is a slide, I think, going back to the slides. Now, I told you that most coals gave you nice straight lines. In his publication, Walker included just one coal that doesn't give you such a nice straight line. Somewhere up here around 100 millimeters pressure carbon dioxide, there's a kink in the curve. So it may become anybody's guess as to whether this extrapolation should be carried out from this portion or whether the original portion has something to do with the volume. There'd be a little uncertainty up here, in other words, as to the BT area for this particular coal, but apparently it's only one in a great many coals that fail to give this complete straight line. And for all practical purposes, one doesn't worry about whether the surface area is off by a factor of 10% or so up here anyhow. But I just wanted to point out that there are a few coals in which this Polanyi-Dubinin plot does not give a single straight line, but puts a kink into it for some particular reason. Now, the first application of coal that I want to make in regard to the surface area has to do with methane adsorption. It is well known that every coal field, at least I think every coal field, has in it a lot of methane. In fact, it's a regular rule to extract methane from coal by pumping down or by putting pipes down into the coal field. You can lead off the methane. The total methane, I think, is about equal to our total natural gas supply. It's somewhere around 200 cubic feet per ton of coal on an average. Well, you can see what this amounts to as a possible source of important gas in the future. But my particular reference to the methane now has to do with the fact, does this surface area offer a possibility of adsorbing all of the methane? 200 cubic feet per ton turns out to be about between 5 and 10% of a monolayer. And this, if I can have the next slide, is just the amount that is observed by adsorption data taken by Anderson, his co-workers, the Bureau of Mines. These adsorption curves at 30 degrees, for example, turn out to be in the neighborhood of 5 to 10% of a monolayer of adsorbed methane. So the first application of surface area is to say that the surface area of coals is high enough to accommodate all of the methane that is found in coal fields, simply by adsorption. You don't have to worry about solubility of methane in coal or anything of the sort. Now, it's true that some of it will be adsorbed in these very narrow capillaries that are down to that are too small to pick up nitrogen, liquid nitrogen temperature, but when the coal expands on heating to room temperature, these get big enough so that carbon dioxide will adsorb in them. So they're probably about 5 angstrom units in size, something of that sort. But they will still accommodate methane and can permit adsorption of methane. So I just wanted to point out that this is the first utility of the surface area. And as far as I know, nobody has yet called attention to the fact that the surface area of all coals, as measured by Walker, are big enough to accommodate all of the methane content that is known. If there are any exceptions to this, I haven't run across them yet. Next slide. Now, you recall I mentioned to you that there were a few bituminous coals that had nitrogen adsorption, liquid nitrogen temperature. Whenever you get nitrogen adsorption, liquid nitrogen temperature, you can use this material in the same way that Barrett, Joyner, and Halinda. And incidentally, I'm using Barrett, Joyner, and Halinda. I recognize that Dr. Roberts here has improved their procedure a great deal. There are other methods of measuring pore size, but theirs was the original, so I'm contenting myself with that, though I think Roberts' work enabled him to put this work on a computer very much more effectively. I don't know if he's in the audience or not, but I'm not slighting him when I just mentioned Barrett, Joyner, and Halinda, because I can't mention all of the people connected with these pore size distributions. Well, any material in which you have adsorption of nitrogen possible, liquid nitrogen temperature, can be used to calculate pore distributions. This is a pore distribution for a particular coal. In the reference, you will find the code number of these. I don't know what PSOC means, but it's something in regard to Pittsburgh coals, I suspect. Number 80. This is shown in the tables and in the data that are included in Walker's paper for which a reference is given. This shows a pore maximum down here in the neighborhood of 30 angstroms diameter, quite small pores, but also shows a considerable pore distribution up here to 200 or 300 angstroms. Now, this would be a charcoal that would have a large pore distribution, not just a small pore distribution. The charcoals that show no surface area at liquid nitrogen temperature, that show surface area when you warm them up, Obviously, the only pores they're going to have are those that were too small to pick up nitrogen, liquid nitrogen, 4 angstroms. They've expanded maybe to 5 or 6 angstroms, but most of the pore structure is very small. But these particular ones that have high surface area at liquid nitrogen temperature have a large pore distribution occurring up here over several hundred angstrom units. Next slide. Just another one. This happens to be one with a double peak, and there's another one of the coals that is included in Walker's paper. Then going back to the transparencies. I don't know whether you can read this or not, and I apologize for it, but it was convenient to take it out of the book without reworking it. All it shows is a partial list of the coals that Walker worked upon and 3 volumes designations. V1 is the volume in pore sizes from 300 angstroms up to 30,000 angstroms, probably gotten with a mercury porosimeter. Volume 2 is in the size range, and these are given in the notes, from 12 to 300 angstrom units. This would be the pore volumes of the type that were shown in these 2 preceding slides, for example. V3 represents the pore volume of this 5, 6, 7 angstrom pores, specifically between 4 and 12 angstroms. Now, if you check this against surface areas, and I'll show you a slide in a moment of the surface area of all these coals, I couldn't put them all on one slide because it was too messy. The V3, this group of coals in here, which have a large V3 pore volume, are all the coals that had surface areas, the V2 pore volume. These that have a large V2 pore volume, this is in the range of 12 to 300 angstrom units, are all samples that had nitrogen surface areas of liquid nitrogen temperature. The V3 area can come from the expansion of pores, and that can be true even when there's no surface area available at liquid nitrogen temperature. Still, in warming to room temperature, it has a considerable volume of these very small pores. But the V2 portion, the percent V2 is in here, these are all from the samples that have a large surface area at liquid nitrogen temperature. At any rate, this gives one a notion as to the total pore volume that exists in these various coals at room temperature, and is one useful item, I think, that one might make use of in any processes which one is going to work at temperatures lower than those at which the coal expands and becomes gooey and forms its own new type of char. Next, transparency. These are simply the surface areas of the materials I just mentioned, and the mess that had appreciable V2 volume are these in here that have from 17 to 83 square meters per gram at liquid nitrogen temperature. Next slide, please. I told you this slide had been misplaced, and it merely confirms the fact that carbon dioxide at room temperature, regular BT measurements, gives you nice agreement with the Dubinin-Polanyi plot type of technique. This is a whole series of coals on which comparison was made between the regular BET high pressure measurements of CO2 and the convenient 50 to 500 millimeter ones using the Dubinin-Polanyi plot. This is merely confirming the fact that we can put confidence in Walker's value for the surface area at room temperature of coal samples that he has given us. Next slide, I think. Now, coming very briefly to the structure of the physical and chemical structure of coal. I just happen to have this slide in place. It's misplaced a little bit. It's a plot that Weiser gives to show the carbon-hydrogen ratio. This comes under the chemical characteristics of coal, so it shouldn't be in this location. But from ratios here where there's less than 1 hydrogen per carbon, all through the various products we're going to be concerned with, clear up to pure methane, which would have 4 hydrogens. The only thing that one would see out of all of this is that one has to put a considerable amount of hydrogen into coal, and this is one of the expensive items to put into coal, to change from coal to any of the products that we're going to use. Next slide. Well, let me pause just for a moment. the only pore structure that I'm going to mention, the only physical characteristics of coal which are mentioned in your notes, have to do with the structure of coal. I believe it's usually believed to be a laminated system, and it has distance between the layers of about 3.5 angstrom units. Now, it's occurred to me that these 3.5 angstrom unit spacings might be the things that are opening up on expansion. I'm not sure whether they are or not, or whether there are extra cracks and crevices that are opening up to give the surface area. But anyhow, it is such a layered structure. It has the pore volume characteristics that I've given you, and I think this is about the only thing I want to cover on physical absorption, or physical characteristics of coal. Chemical characteristics, I've mentioned the carbon-hydrogen ratio that was present. In the notes is given a series of analyses connected with the rank of coal, the carbon, hydrogen, and so forth, but you can read it yourself. I'm not going to bother going through it. So I had to say that as you go from lower lignite coals up to anthracite, one gets higher and higher carbon contents and the usual chemical changes that go along with it. Here's a very brief summary in 3 transparencies, and I want to finish up in the next 2 or 3 minutes, of Weiser's representation of the types of oxygen bonds that exist in coal structures. These are all well known and I think recognized by everybody who's worked with coal. These are the different types of oxygen binding that occur. Next slide. This is corresponding material on nitrogen. These are various nitrogen compounds that are known to be characteristic of bindings that occur in coal. And I think there's one on sulfur if I haven't passed it. Next slide. Yes, these are the various sulfur compounds. And particularly the thiophenes are very bad actors and very hard to remove sulfur. Most of these others lose their sulfur more readily. This, of course, is the organic that we're talking about. In addition, there is iron pyrites, the inorganic sulfur, which constitutes about 50% of the sulfur content. Finally, the next slide is Weiser's compilation of the structure of coal. And I'm sure you've all seen this slide. It's something to keep in mind in connection with all the coal work, that coal undoubtedly consists of groups of several of these aromatic rings, or 6-membered rings anyhow, connected by CH2 groups, in some cases, one or more of them. Sometimes oxygens are binding, sometimes sulfur is binding. But these are mostly small complexes of 3 or 4 or 5, I think an average of about 3 of these rings. And this is taken then as a constitution of a coal molecule. We can just keep it for the sake of illustration. I'm sure that if we could magnify the coal layer, it wouldn't necessarily look like this, but it does contain most of the features that we're going to be concerned with, because in breaking up coal, one certainly has to go after these various bonds, sometimes breaking these bonds, sometimes breaking oxygen, sulfur, nitrogen bonds, but at any rate, breaking these up into smaller groups. We're going to be considering processes that have wound up with about a 30% weight average of benzene from coal. So you can see that these rings eventually can be converted, and we're going to make a point a little bit later, the fact that out of a conglomeration, you get only 1 benzene molecule per conglomeration. In other words, you chew them to pieces on the ends here and wind up with 1 benzene molecule out of the entire group of 3, for example. But we'll come to that later when we consider the definitive treatment of coal. So briefly then, we've studied physical adsorption and chemical adsorption, and have considered the physical adsorption in its application to surface area and pore size, chemical adsorption in relation to the part played by chemisorption in catalytic reactions, and also the use of chemisorption in measuring the amounts of various components on the surfaces of catalysts. Very briefly, we've talked about the structure of coal, physical structure including the pore size that exists in the surface areas of coal, and the principal chemical entities that are in the coal molecule. This, I think, is a good place to stop. I was under orders to make it an hour, and I think I'm just about a minute ahead of time. In a few moments, we'll have a chance for discussion. Time will stop.
Jerry took up a little bit of your time.
Yeah. Hi. We're all ready for questions, I understand. Who's first? Here. I want you to take this.
One of the process reaction modes that we're looking at for coal liquefaction is a carbonization or pyrolysis under hydrogen pressure. How much is known and work has been done on the or physical adsorption of hydrogen on coal to promote the hydrogenation of the coal? And in terms of a hydrocarbonization process, would it be worthwhile for us to look at hydrogen adsorption followed by liquid yields from rapid heating and so on?
So far as I know, there hasn't been any work done on the adsorption of hydrogen for a very obvious reason that the temperatures at which you would get any adsorption of hydrogen on coal are those at which you'd also have reaction between the hydrogen and some of the various bonds that are involved. And you'd probably be getting an indistinguishable mess between reactivity and chemisorption. It'd be very hard to straighten out. But apropos of your work, I can't help but mention the reference I just happened to run across some work from the Dutch workers. I think it was 1959. There's a reference given, or at least I'll have a reference when I come to the lecture, in which they did very much the sort of thing in which I've been interested, namely took coal, protected it by a little bit of oxygen from caking, and then added hydrogen and iodine, adding iodine as a catalyst. And they proceeded to get 35 or 40% liquid product by going not over 350 degrees, which is the temperature range in which you might expect to retain this surface area. So I found it very interesting that somebody, even that long ago, did attempt to make use of some of the surface area that was available by treating with hydrogen using a volatile catalyst such as iodine to get into these cracks and crevices. But as far as the adsorption is concerned, one could make the measurements, but you would have to correct for water vapor form, for hydrogenation of various compounds, and it's be pretty messy. So it would be interesting to see how much hydrogen is picked up under various conditions, but one would have to remember that a lot of the hydrogen would be going to form chemical bonds and probably chemical products, aside from the straight chemisorption. Yes?
Have there been studies made on the effect of either pre-treatment or storage on changes?
Use the microphone. You won't be able to be picked up on the tape, John.
Has there been much work on storage conditions or pre-treatment of coals that could influence the surface areas?
I know nothing on the storage or pre-treatment that would influence surface areas. We are going to a little later come to the question of protecting coal from caking by pre-treating the surface with oxygen. This is something that's very interestingly entered into by surface area calculations likewise. But I won't tell you the results until we get to them. But I do not know of anything having to do with a change in surface area of coal. I suppose surface areas do change with geological times gradually as coal undergoes various types of aging that it may undergo in the ground, but I don't know of any correlations. Specifically, I don't know which coals with respect to age show this surface area, whether this is an indication that bituminous coals gradually change from 1 square meter per gram up to higher square meters per gram as they age or as they're exposed to various conditions of moisture and so forth. I just don't know of any such work on surface areas. The surface area work itself is rather new. This is all published in the last 4 or 5 years, and at least Walker's work has all been published in this time. And I haven't seen any applications of it to any aspects of coal work so far, including the questions of weathering or change in surface area of coal on storage or anything of the sort. Any more questions? It isn't far to walk up here in case you do have to walk up to use this mic.
Professor Emmett, thank you very much for a very interesting and informative lecture, and thank you very much for responding to these questions. I'm sure that there will be other questions for you this afternoon. We're anxiously awaiting your afternoon lecture that will begin in this room at 2 o'clock this afternoon. Apparently, we made only half as many of the handouts as we needed. We'll provide additional copies of lecture number 1 as well as those for lecture number 2 at 2 o'clock this afternoon. See you then.